In this video, we're going to take a look at calculating parametric arc length. So we'll start with a given parametric curve. So here's a Cartesian plane. We'll start at this point, P0, and we've got some curve that cruises along. And it hits different points. So it goes to point 1, then it goes to point 2. So this is the direction, point 3, etc. And there's a distance between these points. So there's distance number 1, and distance number 2, and distance number 3. And if we wanted to find out how long this parametric curve is, all we have to do is add up all of these distances. So d1 plus d2 plus d3, and just keep doing this. And each of these is derived from the distance formula. So the distance that you have for the ith term is the difference in the distance from pi to the previous pi minus 1. And so you have an x direction and a y direction. We take x at time I. We subtract away x at time I minus 1. And we square that value, and then we do the same for the y's. Well, since and therefore, the di from above is equal to x prime ti delta squared times delta ti squared plus y prime ti squared delta ti squared. And this can be simplified to x prime ti squared plus y prime ti squared, and then you can factor out the ti squared, so delta ti, and so the length will be the sum from I equals 1 to n of di, which will be the sum as I equals 1 to n of this x prime ti star squared plus y prime ti star squared times delta ti. And this arc length will be, we'll call it S, will be the integral from a to b of x prime of t squared plus y prime of t squared dt, assuming that x of t and y of t are continuous. So let's take a look at using this final formula. So in this example, we'll show the length of a circle of radius r is actually the circumference, 2 pi r. So previously we learned that in parametrics, a circle of radius r has an x-coordinate, x equals r cos theta, and y-coordinate r sine theta. And so we're going to take the derivative of these two pieces and square them. So negative r cos, negative r sine theta squared plus r cosine theta squared. And so that'll be r squared, and then sine squared plus theta plus cos squared theta. And so this just equals r squared. And so s will be the integral from 0 to 2 pi of the square root of x prime theta squared plus y prime theta squared d theta. And so it's from 0 to 2 pi. I just showed that this is equal to r d theta, and solving this will give you 2 pi r. We can also find the speed of a path. And this can be found by, if you want to know the velocity at time t, then you need to know the derivative of the position function. And so we take the derivative with respect to time t, and then you start somewhere and you go until a certain amount of time has passed of the arc length function. I'll just call this u plus y prime u squared, and it's du. And so this will equal x prime t squared plus y prime t squared. And this step is true by the fundamental theorem of calculus part 2. And so we can use this now to find speeds of all sorts of things traveling along parametric arcs, such as what happens with a particle traveling along the parametric arc defined by 2t and 1 plus t to the 3 over 2. So first, let's see if we can find the speed at s equals 1. And so in meters per minute. And so I get x prime of t will be 2, and y prime of t will be 3 over 2t to the 1/2. And the speed, velocity, so the speed is the derivative, will be the square root of x prime t squared plus y prime t squared. And in this case, that'll be 4 plus 9 over 4t. And this is in meters per minute. And then the speed at 1, velocity at 1, will be about 2.5 meters per minute. For part B, we're going to take a look at the distance that's traveled and the displacement on the interval 0, 4. So the distance is s, which will be the integral from 0 to 4 of, and we can use the equation from before, 9 over 4t, 4 plus 9 over 4t dt, and this will become 8 over 29, 4 plus 9 over 4t to the 3 over 2, evaluated at those two endpoints, 0 and 4, which is about 11.52 meters. So there's your distance, but the displacement is going to be the distance from the original position. And so the c of 0 is going to be at 0, 1, and the c of 4 is going to be at 8, and then 1 plus 4 to the 3 over 2. And we'll use the distance formula on this, and doing just a straight up distance formula will get you 11.31 meters. So you can see that although in this case the path looks something like this, that path length is quite a long way. The displacement is this distance, and it's a little bit shorter. We can actually also find surface area if it's rotated around an axis. So I'll just leave you with that formula. And all we're doing here is essentially creating a surface by multiplying the height and then rotating it around for each value along the distance. And we can create a surface area of, if I took the example before, I can create a surface area of a shape based on the parametric curve when it's rotated around the x-axis. That's it for today.